We've seen that the classical wave equation gives us a way to calculate how a wave might move in response to a given set of conditions, particularly boundary conditions or initial conditions. What I want to do here is talk a little bit about one of the most robust methods for finding solutions to the classical wave equation. Now, I've reproduced the classical wave equation up here at the upper part of the slide, and what I want to do is say, let's suppose we have a solution and we want to try writing the solution as the product of a part that depends only on x and a part that depends only on t. So I want to make it clear that this is an assumption, and I can certainly verify that this assumption works, and that's what we're going to do presently. But it also is possible that the assumption doesn't work. So when you plug this assumption in, if you don't get a self-consistent set of conditions or self-consistent set of equations, then it's not a condition that will work. All right, so now I want to note something about this. I'm going to look at both sides of this classical wave equation one at a time. And if I were, for example, taking the second derivative with respect to x of this new product function, so I'll write that in square brackets, note that this derivative is only going to act on this piece. It will not act on this piece. So in other words, this piece goes unaffected by the second derivative, so I end up with the second derivative of capital X with respect to little x squared. Okay, so that's the effect of that. I'll get a similar result when I take the second derivative with respect to time of this product function. In other words, here this one is unaffected, so it will come out front, and I'll end up with the second derivative of capital T with respect to little t squared. All right, so now when I substitute these things into the classical wave equation, what I'll end up with is something that looks like this. I'll have t of t, d squared x, d little x squared, equal to 1 over v squared, big X, d squared t, dt squared. And I guess I should probably indicate that this is a function of t and this is a function of x. All right, so in this way I have rewritten the classical wave equation, but now for a particular possibility for my solution that is a product of a part that depends only on x and a part that depends only on t. Now what I want to do is take this new version and divide by this product of functions. So if I divide both sides by this product, what will I get? Well, over here on the left-hand side, I'll end up with 1 over x of x, because I've divided out the t part, times d squared x of x, dx squared. And over here I'll have 1 over v squared. When I divide this by when I divide x of x by this product of functions, I'll get 1 over t of t times the second derivative of t with respect to time squared. Now, what I want you to note about this is that with my function, I've got a piece here that is only dependent upon x, and a piece over here that is only dependent upon time. So this method is called the separation of variables method, because by writing the solutions as a product of one variable functions, I'm actually able to create a new equation where I've got only functions of one variable on one side and only functions of the other variable on the other side. All right, so this is actually a pretty clever way to go about. Now I'll remind you again that we're going to assume that the velocity here is a constant. If the velocity was actually a function of both position and time, then we would not be able to do this. We would not be able to separate a part that has only x and a part that has only time. But since we have this equal to a constant, this is a perfectly valid way to proceed. All right, so now how would we deal with this? If I have a part that only depends on x on one side and a part that depends only on time on the other side, what happens as I start varying x? Well, if I start varying x on this side, it means it can't change, because I'm not varying anything on the right-hand side. It is staying the same if I'm only varying x. So in other words, the only way I can have an equation like this be true is if both of these are equal to the same constant. And I'll call that constant alpha. So in other words, if I have both of these equal to the same constant, then I can find a solution for this equation. Now, if that same constant happens to be 0, then I don't have a very interesting solution. In fact, that's something we might call a trivial solution. Okay, but we'll assume that alpha, in this case, is greater than 0. So in other words, I can write alpha as equal to some number squared, because that will always be a number greater than 0. Okay, so how would these two equations look now if I set each of them equal to k squared? Well, if I take the left-hand side here and I multiply both sides, so this is going to be equal to k squared, and I multiply both sides by x of x, I'll end up with a differential equation, and I'm going to draw it like this. That looks like this. Okay, now you'll notice I changed the differentials here. They are no longer partial differentials. Well, I have a single variable in this equation, so now what I have created is an ordinary differential equation. And in fact, this is an ordinary differential equation that is not very difficult to solve. In fact, what I can do is I can show that solutions of the form e to the kx or e to the minus kx will both satisfy this equation. Let's test that out. Okay, let's suppose that I have e to the kx. So I'm going to take the second derivative with respect to x of e to the kx. Okay, when I take the first derivative, when I take the first of the derivatives, and I probably should have left that as a d, not as a partial. Okay, the first derivative of this is going to give me k e to the kx. When I take the next derivative, I'll end up with a k squared e to the kx. So in fact, what I have done is shown that when e to the kx is my function, I get k squared times that function. Okay, I think it's pretty easy to see that the same will happen if I do this with e to the minus x, minus kx. Then I'll get d dx of minus k e to the minus kx, and that will equal k squared e to the minus kx. So both of these are valid solutions. Okay, I'm going to take this a step farther, but we need to go on to a new page. All right, now since both of these will work, I can essentially create what I'll call a general solution that is a linear combination of those two possibilities. So I can write x of x is equal to some constant c1 e to the kx plus another constant c2 e to the minus kx. And this will also satisfy that differential equation. All right, so everything works out pretty well for that. Okay, so in general what we find is that when we have a classical wave equation of the type that we've shown here with constants, we can use separation of variables to convert our linear partial differential equation into two single variable ordinary differential equations. And those ordinary differential equations are things that we can solve fairly readily. And in fact, this kind of solution is fairly typical. Whenever you see something that has a second derivative of a function is equal to some constant, so k squared, times that function, the result will always be of this type. Okay, that will always be the result. So that means that whenever you see that kind of differential equation, you already know the solution. You don't have to do any math. All you have to do is a little pattern recognition.